Hi, welcome to everyone in my multicast series of session. I am Kundan from technical team of Networkers Show. Now I am going to start IP multicast routing. Before moving towards multicast routing, first we will understand the fundamental of multicast. As we know, we have three types of transmission mechanism: unicast, broadcast, and multicast. Broadcast, we have one sender, all others are receivers. Unicast, one sender and one receiver. Multicast, one sender, potentially many senders, many receivers. Why we require multicast? When we are trying to send same data to multiple receivers, in that case, what we require better bandwidth utilization, lesser host router processing, and receivers address unknown. In such circumstance, to get the optimum performance, we are going to prefer multicast. So multicast applications, what we have, transmit the same data at one time to multiple receivers. These are the broadcasts of radio or video conferencing, shared application, advertisement, stock, distance learning, synchronizing of distributed database website. Now here you can say we have one host. Suppose we have three receivers. That's for an example. If we have 100 receivers and one receiver required 1.5 Mbps of speed, 155 Mbps into 100, lots of link bandwidth utilized. So here what in the multicast, source transmit one stream of data for n number of receivers. Replication happens inside router and switches. WAN links only need to one copy of data, not n copies, number of copies. Now, why we are not going to prefer broadcast? Out of multiple users, if certain user doesn't require that particular streaming part, why they are going to engage themselves so that they are not interested in this? So best optimum solution here we have multicast transmission. So multicast distribute information to large audiences over an IP network. As in diagram, we have mentioned one person want to forward this information streaming and multiple users receiving the information at the same time. Only one link is required. So multicast deployments required three elements: the application, the network infrastructure, and client device. IP multicast is a bandwidth conserving technology that reduces traffic by simultaneously delivering a single stream of information to thousands of corporate recipients and phones. IP multicast utilizes a single data stream which is replicated by routers at branch points throughout the network. This mechanism uses bandwidth much more efficiently and greatly decrease load on content servers, reaching more users at lower cost per user. IP multicast is an efficient means of delivering media to many hosts over a single IP flow. So what are the advantages we have in multicast? Enhance efficiency, control network traffic, and reduce server and CPU load. Optimize performance, eliminate traffic redundancy, distribute applications, make multi-point applications possible. For the equivalent amount of multicast traffic, the sender needs much less processing power and bandwidth. Multicast packets do not impose as high a rate of bandwidth utilization as unicast packets. So there is a greater possibility that they will arrive almost simultaneously at the receiver at the same time. So multicast transmission affords many advantages over unicast transmission in a one-to-many or many-to-many environment. Enhance efficiency, available network bandwidth utilized more efficiently since multiple streams of data are replaced with a single transmission. Optimized performance, less copy of data required forwarding, and processing. Distribute application. Multi-point application will not be possible as demand and usage grows because unicast transmission will not scale. Traffic level and flight increases at 1 to 1 rate with unicast transmission. Multicast enables a whole range of new applications that were not possible on unicast, for example, video on demand. That is not possible under unicast transmission. And disadvantages of multicast we have, it is UDP based, so best effort delivery under which heavy drops in voice traffic, moderate to heavy drops in video. Because it is UDP based, so we do not have any congestion avoidance mechanism. It doesn't have duplicate packets may be generated, out of sequence delivery may occur, efficiency is in filtering and in security. There are some disadvantages of multicast that need to be considered. Most multicast applications are UDP based. They result in some undesirable side effects when compared to similar unicast TCP applications. Best effort delivery result is occasional packet drops. Drops are not to be expected. Multicast application must not expect reliable delivery of data and should be designed accordingly. Many multicast applications that operate in real time, like video audio, can be impacted by these losses. Also, requesting transmission of the lost data at the application layer in which this sort of real-time application is not feasible. Reliable multicast application will address this issue. Heavy drops on voice-based voice applications result in jerky, missed speech patterns that can make the content unintelligible when the drop rate gets high enough. Moderate to heavy drops in video is sometimes better tolerated by the human eye and appear as unusual artifacts on the picture. However, some compression algorithms can be severely impacted by even low drop rates, causing the picture to become jerky or frizzy for several seconds while the decompression algorithm recovers. No congestion control can result in overall network degradation as the popularity of UDP-based multicast applications grows. The lack of TCP windowing and slow start mechanism can result in network congestion. If possible, multicast applications should attempt to detect and avoid congestion conditions. Duplicate packet can occasionally be generated as multicast network topologies change. Applications should expect occasional duplicate packets to arrive and should be designed accordingly. Out of sequence delivery of packets to the application may also result during network topology changes or other network events that affect the flow of multicast traffic. Efficient filtering and security for multicast flow is a big issue since sender randomly select UDP ports and very often multicast addresses as well. This kind of behavior prevents effective static filtering. The types of multicast applications we have: one-to-many, a single host sending two or more and number of receivers; many-to-many, any number of hosts sending to the same multicast group. Hosts are also members of group equal to server or receiver. Many-to-one, any number of receivers sending data back to source via unicast or multicast. So there are different types of multicast applications. We have explained earlier also. The two most common models are one-to-many model, when one sender sends data to many receivers. Examples of users of the one-to-many model are audio or video distribution, push media, announcements, and monitoring. If a one-to-many application needs feedback from receivers, then it becomes a many-to-many application, many-to-many model where a host can be sender as well as receiver simultaneously. Example of uses of many-to-many models are collaboration, concurrent processing, distributed, distributed interactive stimulation. Other model, for example, many-to-one, where many receivers are sending data back to one sender, are used less frequently. Example of users of many-to-one models are resource discovery, data collection, auction, and polling. So these are the IP multicast application, live TV, radio broadcast to the desktop, distance learning, multicast file transfer, data and filter, application corporate broadcast, training, video conferencing, video on demand, whiteboard collaboration, real-time data delivery for financial purpose, these things we are. So many new multi-point applications are emerging as demand for them grows. Real-time application including live broadcast, financial data delivery, whiteboard collaboration, and video conferencing. Non-real-time application include file transfer, data and find application, and video on demand. Note also that the latest version of Novel Network uses IP multicast for file and print service announcement. So now we are going to discuss IP multicast address structure. The Internet Assigned Number Authority INA controls the assignment of IP multicast addresses. INA has assigned the IP before Class D addresses space to be used for IP multicast. Class D addresses are denoted by high 4-bit set of 1110. Therefore, all IP multicast group addresses fall in the range from 224.0.0.0 through 239, 255, 255, 255. And the remaining 28 bits of IP address identify the multicast group ID. The multicast group ID is a single address typically written as decimal number in the range 224.0.0.0 to 39, 255, 255, 255. The high order bits in the first octet identify this 224 base address. So now the IP multicast address space separated the following groups. Local scope addresses are addresses 224.0.0 through 224.0.0.255. They are reserved by INA for network protocol use. Multicast in this address are never forwarded of the local network regardless of TTL, and usually TTL is set to 1. What does this mean? These are called 224.0.0.0 to 224.0.0.255 are non-routable. They are not crossing their subnet boundary, their interface boundary. And global scope addresses are addresses 224.0.1.0 to 238.255.255.255. Actually, these are called routable multicast addresses and allocated dynamically throughout the internet. Administrative scope addresses. These are 239.0.0 through 239.255.255 reserved for inside of private domain. These are called private multicast addresses space, which we are using for the host purpose. We will discuss everything in session to session. So multicast delivery is enabled by setting up a multicast address on the content engine in the form of multicast cloud configuration to which different devices configured to receive content from the same channel can subscribe. The delivering device sends content to the multicast addresses set up to content engine, from which it becomes available to all subscribed receiving devices. Well-known addresses assigned by INA 224.0.0 all multicast systems on subnet. The number of my systems, our system like laptop, desktop connected to the switch If they are on the same IP subnet, they are using 224.0.0.1. Directly connected routers interface uses 224.0.0.2. Distance vector multicast routing protocol 224.0.4. OSPF we know 5 and 6, RIP version 2.9, EIGRP 10, PIM version 2.30. And global scope addresses, instance addresses assigned and reclaimed dynamically within applications. Global range 224.0.1.0, 238.255.255, and 224.2.x.x usually used in multicast backbone applications. And these are the routable addresses I have already explained. Part of a global scope address scope recently used for new protocol and temporary users. Global scope addresses are assigned 224.0.1.0 through 238.255.255 and are allotted dynamically throughout the internet. For example, the 224.2.x range is used for multicast backbone application. This stands for multicast band, a collection of internet router that supports IP multicasting. M-Bone is used as the virtual network multicast channel on which various public and private audio and video programs are sent. M-Bone was originated by the Inter-Engineering Task Force, is an effort to multicast audio and video meetings. Some of these addresses has been registered with the INA. For example, IP address 224.0.1.1 has been reserved for Network Time Protocol (NTP). Application that uses multicast addresses 224.0.1.232, 1.2223, and 2.232 range have been demonstrated to be vulnerable for exploitation, which has led to serious security problems. We are avoiding this thing. Addresses in the 232.0.0.0, 232.255.255 ranges are reserved for source-specific multicast. Is an extension of protocol-independent multicast which allows for efficient data delivery mechanism to one-to-many communication. In the next, also another section, we will discuss what is IGMP version 1, 2, 3, how that is going to work, what the advantages of this part we will discuss. So parts of global scopes are used for the new protocol and temporary users. 224.1.00, 224.1.255.255, ST multicast group. Then 2.00, 2.127.253 multimedia conference calls. 224.127.254 SAP version 1 announcement. 127.2.12255 SAP is 0 announcement deprecated. 2.128 to 224.2.255 SAP dynamically assignment. Then we have the 224.250.200, 224.255.255 to DIS transit group, and VMT transit groups are 232.0 to 232.255. That is the for the IGMP version 3 source specific multicast. We have done this thing. So administratively scope addresses are like private IP addresses space. This is used with the boundaries of a single organization. Limited or administratively scope addresses in the range 239 to 239.255 are constant to a local group organization. Companies, universities, or other organizations can use limited scope addresses to have local multicast applications that will not be forwarded over the internet. Typically, routers are configured with filters to prevent multicast traffic in this address range from flowing outside of an autonomous system. Within an autonomous system or domain, the limited scope range address range can be further subdivided so that local multicast boundaries can be defined. The subdivision is called address stripping and allows for address range between smaller domains. These addresses are described in RFC 2365 administratively scope IP multicast. Here we have some example, site local scope 239.255.00, C area 16 and grows down towards to 239.254.16, 239.253. Organizationally local scope 239.192, C area 14. So 239.0010, 239.6410 and 239.128 respectively. And this is the multicast layer 2 multicast addressing. IEEE MAC addresses format, broadcast from multicast brick, and then locally administrated addresses brick. Historically, network interface card on LAN segment could receive only packet destined for their burned-in MAC addresses on the broadcast MAC address. IP multicast, several hosts need to be able to receive a single data stream with a common destination MAC address. Some means had to be divided so that multiple hosts could receive the same packet and will be able to differentiate between several multicast groups. One method of accomplish this to map IP multicast class D address directly to the MAC address table. Using this method, NIC can receive packets destined to many different MAC addresses, their own unicast, broadcast, and range of multicast addresses. The IEEE LAN specification made provision for the transmission of broadcast and multicast packets in 802.3 standard bit. 0 of the first octet is used to indicate a broadcast or multicast frame. The graphic in this slide shows the location of the broadcast multicast bit in the Ethernet frame. The bit indicates that the frame destined group of hosts all network in the case broadcast 0xFFFF. IP multicast make use of capability of sending IP packet to group of hosts on LAN segment. INA owns a block of Ethernet MAC addresses that start with 01 colon 00 colon 5E in hexadecimal format. Half of this block is allocated for the multicast addresses. The range from 0100 5E000000 through 0100 5E7F FFFFF is the available range of Ethernet MAC addresses for IP multi. And this with the range, this MAC addresses have the 21st 25th bits in common. The remaining 23 bits are available for mapping to the lower 23 IP multicast addresses. And remember, there is a 32 to 1 overlap of layer 3 addresses to layer 2 addresses. Be aware that 32 layer 3 addresses map to same layer 2 multicast addresses. For example, all the above IP multicast addresses map to the same multicast of 01 00 5E 01 01 01. What we have mentioned here, everything mapped to the same multicast. So this is the basic concept of multicast fundamental. In the next slide, we will discuss IGMP version, what for the users, what for the routers, everything we will discuss. Thank you.